Hello dear students, welcome to the channel and very welcome to this playlist in which we are discussing about 8051 microcontroller. So up till now we have discussed about the pin diagram, block diagram, details of different pins, different sections of the block diagram in detail. We have discussed about the memory allocation in 8051. We have also discussed about the addressing modes in 8051 and group of different instruction sets in 8051. And in previous class, we were discussing different groups of instructions in 8051, and we have discussed about data transfer group and arithmetic group. So today we are going to discuss about the logical instruction group in continuation to previous videos. So to understand this video, it would be more beneficial if you check out the previous videos. That way you will be able to grasp the information and grasp the concept in a much better way. So I recommend you to check out the previous videos. The link of those videos, the link of the previous video will be flashing on the top right hand side corner of your screen in the I button. You can simply click on it and watch the video out. And also I'm going to include some of the references from previous videos, so it would be more beneficial. But even though if you haven't, it would be fine. You would at least understand the concept. So now that out of the way, let's start with the logical instruction. So in logical instructions again, it would be pretty much similar to the arithmetic instructions and the data transfer instructions, except we will be executing some different instructions from the previous instructions. So first way we are going to discuss will be A and L instruction. On the left we will have destination byte, on the right we will have the source byte, just like previous two instruction sets. And this is the function of logical and for byte variables. So it will perform simple AND operation, right? But it will perform bitwise logical AND operation and between the destination and the source byte. So the result will be stored in the destination byte, which means if I'm taking a comma direct, then the result will be stored in the A or accumulator. The source and the destination support for addressing modes: register, direct addressing mode, register indirect, and immediate addressing mode. Okay, so you can take any addressing mode among these four modes: register addressing mode, direct addressing mode, indirect addressing mode, or whatever what something we call it register indirect addressing mode as well, and immediate addressing mode. And when this instruction is used to modify an output port, the value used as original port data will be read from the output data latch, not the input pins. Okay, always be aware about it whenever you are into the practical or whenever you are executing it in KL, that the original port data will be read from the output data latch and not input. Okay, so many people make this mistake while learning, especially the beginners. So first instruction would be ANL A comma. Let's do one thing. Don't Let's not take every single addressing mode in detail, because up until now I think you we all are pretty much familiar with all different type of addressing modes. So let's only consider one of the instruction mode. Let's take ANL A comma direct. Okay, so I'm not considering ANL A comma RN or ANL A comma at the rate RI or ANL direct A. Okay, let's just see ANL A comma direct. This is a logical AND for byte variable, and it is performing AND operation. So the will bitwise instruction will bitwise logically AND the AND. By mean AND I mean the actual AND operation, if you are familiar with AND operation, and the content of the accumulator with the content of the memory location whose direct address is specified in the instruction. Okay, because we are taking direct addressing mode, and the result will be stored in the accumulator. Okay, because accumulator is a destination byte. So it will this instruction will consist of 2 bytes and 1 clock cycle. We are using direct addressing mode, as you can see, and as simple as that, because we are performing simple AND operation, there is no flag which is getting affected. And I have mentioned an example here. Let's take ANL a comma 50h. So there is 10h stored in the accumulator, as you can see. So, and the content of memory location 50h is C 80. Okay, 80h. And then the instruction ANL a comma 50h will logically end the content of accumulator bitwise the content of memory location 50h. Okay, and result will be stored in accumulator. So see, what do we have in accumulator here? 10h. What do we have at memory location 50h? We have 80. Now what my ANL operation do? It will end them. Okay, so when the end operation is performed, the output or result which you will get will be 0 0, and this 0 0 will be stored where? It will be stored in the accumulator. And this result which is stored in the accumulator, except that there will be no change in the memory location which was involved with the operation or with instruction. Okay, the 80h will remain as it is. Similar way, let's see one more example just to understand it better, because uh, we can perform it without the presence of accumulator as well. Just to understand this, I'm taking ANL direct comma hashtag data. So this is a logical AND for byte variable one more time, and this instruction will bitwise logically AND the content of memory location whose direct address is specified in the instruction with the immediate data. Okay, so result will be stored in the memory location whose direct address is specified, because pretty much we don't have any other options, right? Because we are directly giving we are taking immediate addressing mode for executing this instruction, though you don't have any other option except storing it in the memory which getting involved with the operation. So this instruction will contain 3 bytes, 2 clock cycles, immediate addressing mode, as you all know. Example which we took here is ANL 54h comma hashtag 33h. So what we will see, what immediate data we took 33h. So here we have 33h. Now what memory location did we specified? 54h. So we will check what data we have in 54h. So we have 25. What do we have? We have 25h. So what will we do? We will AND both of them, right? We will perform the AND operation, and when you do it, you you will get an output of 33h, right? Sorry, you will get an output of 21h, not 33h. So you are ending, you are taking AND operation between this 33h and 25h, and it will get stored in memory location 54h. Okay, it will get stored in the memory location 54h. The output is 21h. It is getting stored at 54h because earlier we took the memory we considered memory location 54h for collecting the data from here, and because we are considering direct addressing mode, and the destination is this 54h with the direct addressing mode, the output will be stored in the 54h itself. Pretty much clear. Now let's see next one. This one is different from AND operation. This is XRL a comma RN, and okay, before we go to XRL, there is ORL as well, which will perform OR operation, which we have not considered in classes, because uh, OR operation will perform same operations as ANL. ORL will perform the same operation as ANL, except instead of AND operation it will perform OR operation, except that every other thing will remain same. There will be no change. You will be able to access four addressing modes. The storage of data and memory will data and output will be all same. So now let's see XRL. This is uh, this performs the function of logical exclusive or XOR for byte variables. Okay, exclusive or XOR we call it. So it performs the XOR operation between uh, whatever memory you pick. So it will perform bitwise XOR or exclusive OR operation between destination byte and the source byte, and the result of the operation will be stored in the destination byte. Pretty much clear. Just like always, source and destination support for addressing will be total four addressing modes. Okay, register addressing mode, direct addressing mode, register indirect or indirect register mode, and immediate addressing mode. So same four modes which was getting supported in the AND operation and OR operation will be get supported by XOR operation as well. So when the instruction is used to modify an output port, one more time, the value used as the original port data will be read from the output data latch and not the input pins. Same will happen in the ORL instruction as well and XRL instruction as well. Okay, now let's see the instruction XRL A comma RN, because we previously we saw A comma direct and direct comma hashtag data. This time we will see register addressing mode. So XRL A comma RN is used for logical exclusive or logical XOR operation. An instruction will perform bitwise logical XOR operation between content of the accumulator and the content of the register RN of the selected register bank. So result will be stored in the accumulator. One more time, this instruction contains 1 byte 1 clock cycle without affecting any flags because it is a logical instruction. Let's see an example, XRL A comma R5. So let's say A contains FFH and the R5 contains 15H. Then the instruction will perform the exclusive OR between FFH and 15H, and the content of the accumulator will be lost. Okay, because the output is getting stored in the accumulator. So the output of XOR operation between 15 and FF will be EA, and this EAH is getting stored in the accumulator, and the content of the R5 will remain as it is previously. Clear? Now let's move forward with another one, and this one is pretty much simple. It does not contain complicated things. So this one is called CLRA, and CLR is used to clear the accumulator. So the content of the accumulator will become 0. So basically it means the instruction will clear all the bits of accumulator to 0, and this instruction uses apologies for that. This instruction uses single byte, single clock cycle, and uses the register specific addressing mode without affecting any flags. So let's say if I'm having 77H in the accumulator previously, and when I execute CLR A, then the instruction will clear the accumulator and clear 77 from accumulator, and we will be left with 00 in accumulator. And similar to this, we have CPLA as well. It is called complement accumulator, and that instruction will complement all the bits of the accumulator, which means not complement by mean complement by saying complement I mean one's complement of the number of accumulator will be taken. So bits will previously containing 1 are charged to 0 and 0 will be charged to 1 or vice versa. So if I'm having 57H in accumulator, then how will you convert its ones complement, because it is in a hexadecimal, so you have to first convert into the binary. So we will convert hexadecimal into the binary. 01010111b would be the binary form of 57H, and when you take the ones complement of it, you will get 48 in the hexadecimal. So 57 will be converted in the 48 in hexadecimal. Now let's move forward, and let's move forward from the logical instructions to Boolean variables or Boolean instructions. Although there are plenty of logical instructions are there which you can learn or perform, but I will leave those instructions up to you, because these instructions are most useful instruction, and other instructions from these instructions you will be able to grasp and learn other instructions pretty easily, right? There is a rotate accumulator left through carry RLC instruction. Then we have RRA instruction, rotate accumulator to right instruction. We have swapping instruction. We have RRC through carry. So we have so many instructions. But now, for now, let's move forward with the Boolean variable manipulation instructions. So first one is a CLR bit. Previously we saw CLR accumulator. We now are saying CLR bit. So this will clear out the bit which you are going to use, right? So instruction will clear out the indicated bit, and CLR can operate on carry flag or any directly addressable bit. It contains 1 if carry is specific and 2 if directly addressable bit. Okay, it contains 1 byte if carry is specific, and it contains 2 byte if directly addressable bit. We are dealing with directly addressable bit, but in both of the situation it will contain only 1 clock cycle. Now about addressing mode of the CLR bit, and the whole all the instruction in the Boolean variable manipulation instruction, it is a bit complicated. If operated on the carry flag, then register addressing mode will be used, and if not operating on the carry flag, we will be using direct addressing mode. Okay, if you are using a carry flag, because we are using carry flag, that means you are including special registers, right? So you have to use register addressing mode. But if you are not using the carry flag, then you can operate it on direct addressing mode. Again, when it comes to flags, only carry flag will be activated. And when we come to seeing an example of it, let's say port 2 has previously been written with A5H, and the instruction CLRP 2.3 will clear the third bit of port 2, leaving port 2 with A5H. Okay, so one more time, if instruction CLRP 2.3 will get executed, then it will clear the third bit of port 2. Okay, it will clear third bit of port 2. Okay, so that was the CLR bit. Now let's see next one, CPL bit. So this is a complement bit. The instruction will complement the bit variable specified, and a bit which had been a 1 is changed to 0 and vice versa. Simple ones complemented you will be getting. And CPL can operate on carry flag or any direct addressable bit. The byte it contains will be same as previous. It will contain 1 byte if carry is specified, and it will contain 2 byte if directly addressable bit is specified, because If you specify the carry, we are operating on the register addressing mode, and in register addressing mode you always operate in single byte. And if you are not containing carry, then you will be operating in direct addressing mode, and it always operates on 2 bytes. Either ways, you will always be using one clock cycle, and there will be only carry flag which will get affected. And for example, let's see port 2 has the previously has been written with A5H. So the instruction CPL 2.5 will complement the fifth bit of port 2. Okay, the instruction CPL P 2.5 will complement fifth bit of second port, and uh, that complement will be stored in the port 2 itself. Okay, so if it was containing A5H previously, now taking the complement of fifth bit, what do you have? You will have 85H. Okay, now let's see one more, and the last one is the boolean, because we don't go into the detail of the boolean. If you want me to, please mention that in the comment section below, so I can understand, and I will explain boolean in detail as well. So third one is the move c comma bit. So it moves the bit data, and it is simple move operation. You know how move operation works, right? So the instruction will copy the data from boolean variable whose address is specified in the instruction to the carry flag. Okay, c here stands for carry, and bit is data from boolean variable whose address is specified in the instruction to the carry flag. If it doesn't make sense, it will make sense when we take the example, but before that, let me tell you, the instruction will contain 2 bytes, 2 clock cycles, and it will always operate in the direct addressing mode. And again, the flags which will be activated, only the carry flag will be activated, and of course it makes sense because you are working with carry flag here, right? So for example, let's say move c comma acc4. So let's say carry is 1, which means c is 1, and a has a 0 1 h, or accumulator has 0 1 h. Then the instruction move c comma acc4 will load the content of the fourth bit. Okay, it will load the content of the fourth bit of accumulator to the carry flag. Fourth bit of accumulator to the carry flag. Now see what is the fourth bit of accumulator when you convert 0 1 h into the binary. And binary, when you convert into the binary, you have to convert it into the base of 8, because accumulator is an 8 byte register. So what you will get? 7 zeros and 1, because it is containing 0 1 h. So the what is the fourth bit? Counting from here, you will have 0. So you will be left with carry is equals to 0, leaving c is equals to 0. So that was our boolean variable manipulation instructions. We saw 3 of them. If you want me to discuss about them in detail, please mention that in the comment section, so I will make a video on it. And this boolean variable is also our fourth type of instruction set, which we mentioned earlier. We called it program based. So this is pretty much that. And fifth one, or last one, last addressing mode, I mean, would the program and machine control instruction, or program control instructions. And we are not going to see many examples of it, because we don't go into that much detail. We don't have that much time. If you want me to make a video on it, please tell me. I will make a video on it, but that is not part of your syllabus, so we are not going into the detail. We are just going to see one example, and that example too, because I want you to understand about a specific addressing mode which we are using in this case. If you remember, jmp at the rate a plus dptr, right? It is a jump indirect function, and it will perform the jump instruction, but there is more to it than just simple jump instruction. See, when we discussed about the addressing mode, we saw this index addressing mode. and it contained only one instruction, and that was this one. So here we are going to use the index in addressing mode. See, we already saw all these addressing modes in detail when we discussed different instructions in previous three videos and in today's video as well. But we haven't seen the index addressing mode up till yet. So this instruction includes the index addressing mode. So what this instruction will do, so this instruction will add the 8-bit unsigned content of the accumulator with the content of 16-bit data pointer. Okay, so what will it do? It will add the 8-bit unsigned content of accumulator with the content of 16-bit data pointer, and the result of the addition is loaded into the program counter. Okay, so this is the most weird and most complex instruction which you will see. What are you doing? You are taking the 8-bit unsigned content of accumulator, you are taking the content of 16-bit data pointer, you are adding both of them together, and this addition is getting loaded into the program counter. So this will be the address from where the microcontroller will begin execution. Okay, and neither the accumulators nor the DPTR or data pointers content are getting altered. Okay, so the content in the accumulator will remain as it is, content of data pointer will remain as it is, but the result will be stored in the program counter this time. So this is a single byte instruction, but it contains 2 clock cycles. It does not affect any flag, and let's see an example of it. Let's say accumulator contains 30H, and I'm saying 30H because it is in 8 by 8 bit unsigned content that we want. Then data pointer contains 1000H, it is a 16 bit data pointer contains 16 bits, so 1000H, and program counter 0500H. So the instruction JMP at the rate A plus DPTR will, the program counter will contain the sum of content of accumulator and data pointer. So add 1000H with 30H, you will get 1030H, and this 1030H will be loaded into the program counter, and execution will begin from location 1030H instead of location 0500H. Are you understanding? Because remember, what is the function of program counter? It points the memory address and executes it from there. But previously program counter was what was indicating 0500H. So the execution of instruction was about to get start from 0500H, but now that we have used this instruction JMP at the rate A plus DPTR, A had 30H, DPTR has 1000H, and when you are taking sum of it, you are getting 1030H. And this 1030H is, where is it going? It is going into the program counter. So now instead of 0500H, program counter is indicating 1030H, and whatever instruction was about to getting executed will now get executed from memory location 1030H instead of location 0500H. Clear? Another example or application of this instruction is in the case jumps. You can see this jump table here. We use move dptr hashtag jump tbl, then index number is getting specified, and then we are using this instruction, and here we have the jump table from case 0 1 2 3 4. So if index number is 1, data pointer is 1000, accumulator contains 0 1, then execution will begin from address 1001 in case 1. Clear? So we will keep today's class till here, and next time when we meet, now that we have discussed about every single instruction set and every single addressing mode in detail, So next time we will start something new, most probably stack pointer. But let's see. I have to check. So we will keep today's class till here. If you have any doubts, queries, questions, or any suggestions, please mention that in the comment section below. If you have any queries, please mention them. I will try to answer them as soon as possible. If you have any feedback, anything related to the channel, videos, playlist, or any suggestions, if you want me to make a video on certain topic, certain subject, please mention that in the comment section below as well. I will see them. I will try to do it. I will see what I can do. So please mention that in the comment section as well. If you have any suggestions, mention them as well. So I will be seeing you next time with a new topic. Till then, take care of yourselves. Keep watching. Please subscribe. And thank you very much for listening. Goodbye for now.